the third and final part of this mini-series of tutorials on algebra. And in this final tutorial, we're going to look at rearranging equations, which is a topic that I just know many students have difficulty with. And it's such an important skill in doing maths, particularly if you use mathematics later on in science or in economics or in other disciplines. You need to be very able to sort of use equations like a potter would use clay to mold it. And so you need to be able to put your hands on an equation, shift it around very confidently and correctly. You mustn't make errors when you rearrange equations because they cease to be equations if you do that. So the purpose of this tutorial is to start with some very simple examples to show you how you can be sort of speedy and confident in moving things around. And then we'll just look at a few examples from my home discipline of physics where we can see why you might want to rearrange an equation and how we would go about rearranging certain equations. So let's start off though with some really simple examples. So let's say that we had an equation x plus 3 is equal to 5, and we wanted to solve this equation for x. Just by looking at this, you can see that the answer is going to be x equal to 2 because 2 plus 3 is equal to 5. How would we go about sort of demonstrating that? What we want to do is subtract 3 from both sides of the equation. So if I subtract 3 from the left-hand side, I'm just left with x. So let me just put in brackets here, sort of to the side, I'm subtracting 3. So subtracting 3, then left-hand side I have x, right-hand side I have 5, take away 3, and then I have x equal to 2. Now, I've said explicitly we're taking 3 away from both sides of the equation, but sort of a faster way to think about this is to say that we're moving this 3 to the right-hand side. But do you see that moving plus 3 over the 3 picks up a negative sign? Let's do another example. Let's imagine we have y plus 4 is equal to 7. Well, I want to subtract 4 from both sides. Subtracting 4 from the left-hand side, I'm left with y. And then I have on the right-hand side 7 minus 4, and I'm left then with y equals 3. And again, you see that 4 moving across essentially has picked up a different sign. So the way to think about this, you can laboriously say I'm going to subtract 3 from both sides, or I'm going to subtract 4 from both sides. But let's just do another example the speedy way. Let's say I have a symbolic equation, x plus a is equal to b, and I want to express this in terms of x alone. I'm subtracting a from both sides, but I can speedily think I want to move a across the equal sign. And when we move a quantity across the equal sign, then it picks up a different sign. So a comes across and it picks up a negative sign. And I have x equals b minus a. If I had another example, let's say I had x minus, let's say c is equal to f, for example, and I want to express this in terms of x, I'm effectively adding c to both sides of the equation. Another way to think about it is this c is carrying a negative sign. When I move it across, it's going to change sign and pick up a positive sign. So I will have f plus c. So if you have a term in an equation which I'm going to call additive, meaning it's just standing alone on one side of the equation with nothing multiplying it, you're perfectly free to move it to the other side of the equation. You just have to remember that it needs to change sign as you move it across. So let's just do one more example. Let's say we had z plus 2 minus, let's say, g is equal to 5, and I want to express this equation in terms of z or z. I need to move both these terms over. The g is carrying a negative sign. When I move it over, it's going to become plus g. The 2 is carrying a positive sign. When I carry it over, it's going to take a negative sign. So I'll have that z is 5. I'll take the 2 over first. That gives me minus 2. I'll take the negative g over. That becomes plus g. I can simplify, and I'll have that z is 3 plus g. Now, that's when you have terms that are standing alone in an equation with nothing multiplying them. Often we have multiplicative terms in equations, so we might have something like this: 3x equals to 7. In this case, we want to divide by 3. That's the operation that we want to perform. And if we divide both sides of the equation by 3, we'll have 3x over 3 on the left-hand side. And on the right-hand side, we'll have 7 over 3. From your fractions, you know that 3x over 3, we have a common factor of 3, it cancels out. So we're left with x equals 7 over 3. Let me just do another example. Let's have a symbolic one. Let's say we have a times y is equal to b, and I want to express this equation just in terms of y. I want to divide by a on both sides. So I'll have divide by a on the left-hand side and divide by a on the right-hand side. Have a common factor of a. Those cancel out, and I'm left with y equals b over a. Now, again, this can be quite tedious to sort of spell out exactly what operation you're performing. You really want to be confident to move the symbol across. So when I move a multiplicative factor across the equal sign, I have to make sure that I essentially have nothing else around on that left-hand side, in this case, that is going to be effective. So it needs to be a complete prefactor, nothing else around that is not multiplied by the 3. And then I can just literally bring it down onto the other side. So something that's multiplying on the left-hand side can be brought down into the denominator on the right-hand side. So this a is multiplying the y on the left-hand side. There's nothing else around, no bystanders as it were. I can bring it down to the right-hand side into the denominator. It may have been confusing what I was saying about bystanders. Let's do this example here, but let's say there was another term hanging around. Let's say plus c equal to b. Now, I can't just take a over to the right-hand side in the denominator because this term is not multiplied by a. So if I divided everything by a, you know, it's a bit messy. I would have y plus c over a is equal to b over a. So here, even though I want to divide by a, I need to just prepare the ground. I want to make a something that is the only multiplicative factor on the left. So, first of all, get that term across. So first of all, take c across. It's carrying a positive sign, so we're going to change its sign as it moves across. And now, on the left-hand side, there are no bystanders, as it were. A is just multiplying y very cleanly. We can bring the a downstairs. Notice how it will be a denominator for the entire right-hand side. So to stress that, I'm just putting brackets around the b minus c to stress that both of these terms are divided by a. Let's just do one more example. Let's say that we have 5x minus 2 equals 3x plus 4. I want to solve this equation for x. Well, I want to first of all move this over here so that I can combine this term with x with this one. And I also want to get rid of this bystander term. If I ultimately want to sort of solve this equation for x or express the equation as x equals something, I need to get rid of that term. So I'm going to move this over here and this over here. So the 3x comes across the equal sign, it changes its sign. The minus 2 goes over and it changes its sign and becomes plus 2. I then have that 2x, 5x minus 3x is 2x, is equal to 4 plus 2 is 6, and so x, now dividing by 2, that 2 comes downstairs, is 6 over 2. So finally I have x equal to 3. Something that I haven't stated explicitly, but is the golden rule of manipulating equations, is do to the left-hand side, and we sometimes abbreviate left-hand side to LHS, do to the left-hand side as you do to the right-hand side. And this really is sort of an implicit rule about manipulating equations. An equation means that the thing on the left in total is equal to the thing on the right in total. There's a balance between those two sides. The equation only remains an equation if you start tinkering with it, as long as you always do to the left as you do to the right. So subtracting 3 is fine as long as I do it to both sides. Dividing by a is fine as long as I do it to both sides. So everything you do to an equation you must do to both sides. Let's do another example. Let's imagine now that we have 2 over x is equal to 5, and I want to know what x is. This looks a bit ugly, doesn't it? Because the x is kind of on the bottom. How would we go about this? Well, there's different ways that you could do this, actually. You could, if you wish, multiply both sides by x, which effectively, let's just do that explicitly. If I multiply both sides by x, I would have this common factor of x. I'm left with 2 equals 5x. I'm always free to write an equation sort of backwards, so I can just write that 5x is equal to 2. I can sort of write the equation as if I was reading it this way. I can divide by 5 and I would have x is 2 over 5. Bring that 5 downstairs. Maybe a faster way of doing this, though, would be to say, let me just flip both sides of the equation. Okay, so I want to just invert both sides of the equation. In slow motion, what I'm doing is actually dividing into 1 both sides of the equation. So I'm essentially saying 1 divided by 2 over x is equal to 1 divided by 5. Okay, so what am I doing to the left-hand side? I'm dividing it into 1. What am I doing to the right-hand side? I'm dividing it into 1. Doesn't matter what the operation is, as long as I do to the left-hand side as I do to the right-hand side. This looks a bit odd, but remember your confidence with fractions, that 1 divided by a fraction, so I'm just thinking about the left-hand side here, 1 divided by a fraction is like 1 multiplied by the fraction flipped. So whenever you see 1 over a fraction, you can immediately write it as the flip of the fraction in the denominator. Okay, so 1 over 2 over x. Be confident, remember your fraction division rules. It literally means 1 divided by 2 over x. We know that's 1 times the flip of that fraction, x over 2. So 1 over 2 over x is x over 2. We have this equal to 1 over 5. Multiplying there by both sides by 2, effectively this goes upstairs to here. And you see, we have the same answer. This looks like a complicated example, but actually with confidence you'll be able to go straight from here to here. you have the thing you want in the denominator. You're essentially flipping both sides. You're remembering from some early tutorials that an integer 5 can be thought of as a fraction, 5 over 1. You're flipping that, you're flipping this, and then you're multiplying both sides by 2. But the speedy way of thinking it is you're moving the 2 upstairs across the equal sign. Just as we brought a downstairs across the equal sign, something in the denominator can be brought upstairs, just as we saw here. We move the x upstairs. So 2 different ways of solving that problem where x was sort of in the denominator, but again, just involving confidence in manipulating the left-hand side exactly the same way as the right-hand side. So let me just do a few examples from physics, which will just aid because there'll be more examples, but they'll also give you a confidence that yes, it's important to do this because you can, get useful information from science problems this way. Let's start with a simple example. We know from basic physics that the speed or the velocity is equal to the distance travelled divided by the time. So if you know the distance something has travelled and you know the time, you can calculate the speed. Sometimes, however, you might have a different problem. You might know the speed of something and you might know how long it's been travelling for, and you'd like to know how far it's travelled. So how would we get the distance from this equation? Well, the slow way is to sort of multiply by t, but essentially we want to isolate the distance. So we just move this variable upstairs on the right hand side. So we should be confident saying that v times t is equal to s, moving that upstairs. And that would be the solution to our problem. The distance is the speed times the time. Alternatively, you might know the speed of something and you might know how far it's travelled. You want to know how long it took. You want to isolate t. Probably what you would do then is this step, you would move t upstairs to the left-hand side, and then to isolate t, you want to get rid of this v and take it downstairs. And so t from here would be s divided by v. You just take the v downstairs on the right-hand side. Another equation from physics is what's called the lens equation. And you have something called the focal length of a lens is given by 1 over the object distance plus 1 over the image distance. So this is an equation from optics. But for our purposes though, imagine that someone had measured the object distance and the image distance and they wanted to have a formula for the focal length that's a bit simpler than this one, because this looks a bit awkward with the focal length in the denominator. So how can we write this as f equals something? Well, probably the easiest thing is to simplify the right-hand side. Remember your fractions. These are just 2 fractions added together. So when we add fractions, we take this upstairs, we take this upstairs, and we multiply by the product. So we have 1 times v plus 1 times u divided by the product of the 2 denominators. So this equals v plus u over u v. And now the easiest thing to do is just to flip both sides, just like we did over here with this one. So I want an equation for f, no problem. I'll just flip the left-hand side because it's expressed as a fraction, and I'll flip the right-hand side. So this is a nicer form of the equation if I just want to have a quick way to calculate the focal length if I have both u and v. Let me do one more example. If you have a pendulum which goes back and forth, and let's say the length of the pendulum is L, and it's the mass of the pendulum is experiencing the acceleration due to gravity of little g, there is a nice equation that tells you what the time is for the pendulum to do one full cycle of an oscillation. We call that the period in physics. The period would be given by 2 times pi times the square root of L over G. So let's say that you knew what G was, 9.8 meters per second on planet Earth. You measured the period of the pendulum and you wanted to therefore calculate the length of the pendulum. How do we isolate L in this equation? This is quite tricky because L's hiding inside a square root. Well, we need to sort of strip away things bit by bit. First of all, we have to get rid of this 2 pi. So let's take the 2 pi downstairs. Across the equal sign it goes downstairs. And then we have this. But now the thing we want is still under a square root sign. How do we get rid of a square root sign? Well, we square both sides. So if I square the left-hand side, I'll have t over 2 pi times itself, so t squared over 4 pi squared. And if I square the right-hand side, the square root times the square root is by definition the thing inside the square root, L over G. And finally, I want L by itself. I can move this G across, and so I would have that G t squared over 4 pi squared is equal to L. And that way I have the length of the pendulum in terms of the gravity times the period squared. Alternatively, you might have this pendulum, let's imagine that you landed a probe on a distant planet, let's say it was Pluto, and the probe wanted to measure the acceleration due to gravity on Pluto, and there's probably better ways of doing it, or maybe not, I don't know. Let's say it has a little pendulum and it just measures the period of the pendulum of a known length, and you want to measure little g, the acceleration due to gravity on Pluto. Well, we've almost got what we need here, but g is in the denominator, so we'll just flip both sides. So on the left-hand side, we flip it. Effectively, we're dividing it into 1, but the equivalent thing is to flip it upside down, and then we flip this to g over L. And now I just want to multiply by L. Take L upstairs on the right-hand side, and that gives me g. So this would be the formula that the little Pluto rover would be using, knowing L and measuring t, to send back to Earth a value for acceleration due to gravity on Pluto. So these are very sort of important examples from physics. I chose one from dynamics, I chose one from optics, I chose one from mechanics of pendula, where you have an equation that relates different quantities to each other, and you need to rearrange equations depending on what you actually know. So in this equation here, which relates 3 things, if you know the object length and the image length, you might want some very simple equation that directly gives you the focal length. Here, you might know, say, the velocity and the distance and need to know the time. So you want to quickly rearrange this well-known equation to this less well-known equation to give you the time in terms of the distance and the velocity. This example, which relates the period of a pendulum to the length and the acceleration due to gravity, depending on what information you have to hand, you might want an equation for the length, you might want an equation for the acceleration due to gravity, and you need to be quite comfortable sort of getting your hands on the equation, manipulating it, and you will not go wrong as long as you do to the left-hand side as you do to the right-hand side. And this part of the tutorial over here is really just to kind of give you confidence in being speedy, taking things across the equal sign. If they're additive, they hop over the equal sign and they just change their sign. If they're multiplicative, they hop over the equal sign and go into the denominator of the other side. If they are things that are divided, they go across the equal sign and end up in the numerator. So x in the denominator here ended up in the numerator on the right-hand side. T in the denominator here ended up in the numerator of the other side of the equation. This final example was more complicated. Here we had to kind of strip away to get the thing we wanted, and we even had to take the squares of both sides to get rid of a square root. But again, students have all of the knowledge to do this. They just need the confidence. You need to invoke your fractions knowledge, some algebra knowledge. You have all the skills. You need to be confident and obey the golden rule. Do to the left-hand side as you do to the right-hand side. The one, to end the tutorial on a negative, the one exception when you must not do this is divide by 0. You are never allowed to divide by 0 because it does not have a meaning in mathematics. It immediately makes both sides invalid. And so you can essentially blow up an equation by dividing both sides by 0. But apart from that one thing, it's like the Bluebeard story where his wife was never allowed to look into one room. The one thing you're not allowed to do with equations is divide by 0. But anything else is okay as long as you do to the left-hand side as you do to the right-hand side. So I hope this is helpful. I mean, as with so many things, you need to practice to get an agility with this. But I hope that this tutorial gives you some inspiration that it's not really that difficult, that with a bit of practice you can become very speedy and confident with this, and you'll feel very empowered to see equations as clay to a potter and manipulate them for your own purposes. So I hope that's helpful, and I'll see you next time.